Okay, for our last video for this particular chapter, this is a big one, right? I'm going to preface this. I'm going to start us off immediately by saying this is one of the biggest things that you need to understand to get through this class. Homeostasis, right? You will have a very difficult time getting through this course if you don't have a decent understanding of this. And that is because all the things we're going to talk about, all the different processes we're looking at throughout the semester are rooted in this concept of homeostasis. They're rooted in this. So you really need to pay attention to this, understand it. And if you don't understand it, contact me, go to tutoring, go to something, because you need to know these feedback loops. You need to know these things because everything we're talking about throughout this course, for the most part, is some process that is used to get us back to homeostasis, to get us or to keep us in homeostasis, right? So really, 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 really important, especially because when we leave homeostasis, we leave that set parameter, that's when we start being ill, right? We start feeling sick, we start having a problem, right? When we leave that normal range. So with this, I mean, I'm hammering it in now. I hope that if you're listening that you are really paying attention to this, because you will not have an easy time in this class if you do not understand this concept. You don't need to understand it perfectly right away, but you do need to make an effort to understand it as best as possible. Again, if you don't understand it, ask, right? And we'll figure something out to try to help you get there. But this can either really help you or hurt you, right? If you understand it, it's going to help you. If you don't understand it, it's going to hurt you. So we're going to talk about that for the bulk of this video. We're also going to get into some definitions, mainly symptoms and signs, talk about what those are, that there is a difference between them. And then we'll talk about some normal reference ranges and that basically how when we escape those ranges, we're too high, too low, or whatever, how that results in something like a disease or a disorder. So I just said, right, I spent forever talking about how important homeostasis is. It's so important, right? But what is it? It's kind of hard to say this is really important without actually telling you what it is. So I'm going to read the big thing here, and then I'm going to sum it up nice and neat for us. So what our book basically says, or what our lecture says, is that homeostasis is the condition of equilibrium in the body's internal environment produced by the interplay of all the body's regulatory processes to correct deviations, also known as changes, in either the external or internal environment. That's a lot of words, right? If we're honest, right? That's a lot. That's really bulky. But we can sum it up very nice and succinctly. That basically homeostasis is the maintaining of a relatively constant internal environment. That's our quick and dirty. We want to maintain, right? So we want to keep a relatively constant. So relatively constant, we mean there's some fluctuations. It doesn't have to be set on one single point, but we don't want to stray too far. Internal environment. So the body, right? We want to maintain certain parameters. The external environment may change, right? That's fine. We don't need to change the external environment, but we do want to maintain the relatively constant internal environment. We want to maintain something we want to regulate, right? We want to keep a very set, very tight set of ranges. We don't want to stray too far in either direction. So homeostasis, right? Again, it's self-regulation, and you're not staying on one single point. It's dynamic, meaning we have movement. You're going to move within that range, and that's normal, right? As long as we're staying kind of balanced. It's like if you were walking on a tightrope or a balance beam. You're not staying in one single point, and you're not slowly shuffling your feet forward, never wiggling to the left or right? If you go across something like that, you're probably going to wiggle a bit, right? You're going to tilt to the left and tilt to the right, but what do you do when you tilt to the left? You try to bring yourself back over to the right. And what do you do if you go too far to the right? You bring yourself back towards the left, right? And you keep doing that, so you stay relatively in the middle, but you're not expected to go in a perfectly straight line, right? As you cross, your body's going to move a bit from side to side as you go. So that's what we mean with homeostasis, right? And if you swing too far, right, if you're on a balance beam, you really swing to the left, you may fall off, and that's a problem, right? So homeostasis is trying to prevent us from falling off that balance beam. We don't need to be in an absolutely perfect straight line. We just have to stay straight enough to be able to keep going across, right? And so that's what we mean with homeostasis and dynamic equilibrium and self-regulation, is that our own body is going to be causing little fluctuations to keep us somewhere in the middle, right? That's what we mean by that. So we want stability, right? But not necessarily perfection. So throughout this course, we're going to be talking about all sorts of different processes that are used to maintain homeostasis, to make sure that we're not leaving that normal range. And it gets a little complex, and obviously with this course, we're going to get into some detail, right? We're going to definitely get into way more detail than we did in something like Bio 5. We will not get as crazy as we could. This does get more detailed than this, so keep that in mind. We are doing a slightly simplified version of this class to some degree, but definitely more difficult than what you've had in the past, more than likely. The big thing though is when we disrupt homeostasis, meaning we leave the normal range, we're too high, too low, whatever. This is when we see disease. So we will feel it. We will feel ill. We'll feel sick. And if we keep going, we can potentially die. Right? Now, it's really important that you're able to define homeostasis in your own words. Right? Don't just regurgitate this on something like an exam. Don't just spit out what I've said here. Write this down in your own words, because you're going to need to know this definition. You're going to be asked about it. I can tell you that much, especially on something like a quiz or on like an exam. Right? You are not going to escape this class without having to explain homeostasis over and over and over again, and you better be able to do it in your own words. So what are the components? When we're trying to maintain homeostasis, what are the things involved with allowing us to do that? The big thing is what's called a feedback loop, right? And so for the most part, we're going to be talking about a negative feedback loop. The negative feedback loop is not a bad thing. It's a very good thing. We'll get into it in a little bit. But no matter what feedback loop we're looking at, whether it's negative, positive, whatever, there's some main kind of moving parts. We have the receptor. This is going to tell us that something has changed. Right, so let's say we're talking temperature. We're going to use temperature as an example here. The receptor is going to tell us the temperature has gone up or the temperature has gone down, right, whatever. Or some sort of stimulus, like we've lost some sort of balance. So we've detected something has changed in our environment, either internally or externally. We have a control or an integrating center, right? So this is basically taking the information from the receptor and then making sense of it, right? So we see, we have a receptor that detects a change in temperature. The integrating or the control center is going to then go, okay, we notice there's a change in temperature. This is a very big change, so we need a big reaction, or this is a small change, we don't need to do much, or we don't need to change at all. The control center is then going to make the decision of what to do. So let's say the temperature has gone up. Right? Receptor says, hey, temperature's up, right? It's at the time of recording, it's August. It's really hot out, way, way hot out. I walk out of my air-conditioned home into the summer heat, and my control center goes, whoa, it's toasty out here. What am I going to do about this? Because if I stay out here in this heat and do nothing, body temperature is going to go up to a dangerous degree. I don't want the body temperature to go up to a dangerous degree. So the control center is going to then figure out, well, what do I need to do to make sure body temperature stays relatively normal? That's where they send a signal out to what are called effectors. Effectors are going to cause a change to keep us in the middle, right? Or bring us back to the middle. So we're talking about body temperature and being in a hot environment. In this case, effectors can be something like my sweat glands. Right, so it's really hot out. my body temperature will continue to rise if I do nothing. So we then send a signal to my sweat glands to release sweat to have a cooling effect. The sweat glands release their sweat, the cooling effect takes place, and so my body temperature stays within a normal healthy range, even though the outside temperature might be 105, right? I can still stay in a healthy range because I have these mechanisms in place to keep me there. Some other things that we need to, some terms we need in order to describe the feedback loops are things like stimulus. This is just a detectable change that has happened either internally or externally. So like the temperature change that we talked about. I walk out of the air-conditioned room outside into the summer heat. We have the variables. These are the parameters that are monitored by the feedback system. So things like temperature or blood pressure. The receptors, sometimes called sensors. So you may see either. Now, if it's an open writing question, like a short answer or essay type question, you can use either of these terms. I'll know what you're talking about. I will stick with receptors just because that's the main one we have there. This is going to detect change in the variable. So it's going to detect, for example, when the temperature changes, right? If it gets too high. The control center, this is going to compare the variable in relation to a set point. So think of the set point as like your thermostat, right? You set your thermostat to a certain temperature, right? So like I look over at my thing right now and it's set to like 74 degrees, let's say. So my set point is 74 degrees. But there's a normal range. It's going to take a little bit before my AC kicks in, right? As soon as I go 1 degree over 74, it's not necessarily going to kick in, right? Or if it's 74.1, right, or 74.2, it's not going to automatically kick on the system. There's a range, and once I leave that range, then the AC will kick on, right? So the control center is kind of making the decisions of where is the thermostat supposed to be set, what's our set point, and how far do we need to deviate from that set point before we see us needing to impact this, to cause a change to bring us back to normal. Effectors, I already mentioned on the last one, but just as a kind of drive it home, these are the parts of the body, organs, tissues, whatever, that will do the things needed to cause a change. So glands, muscles, right, those types of things. And then communication. It's extremely important for communication that either nerves, so the nervous system, or hormones from the endocrine system are going to be in constant communication here to keep us in that middle ground. That way we don't go too far, right? We don't overcorrect to a point where we can hurt ourselves. So think of it like if I was in a really hot environment, right, and I shifted, there's a few things that go on there. If it's really hot, I start to sweat. I will change a little bit in terms of blood flow to pull blood up towards the surface of the skin to dissipate heat while I sweat. But if I give there's no control, I just go for it, sweat, and I never tell it to stop, or I never say how much sweat, right, is normal. Like that can be a problem. So constant communication is required so that we don't have a runaway train type of thing where we overcorrect and now we're stuck in a position where we're on the opposite end. We've gone from too high to too low to a dangerous degree. And so here's our kind of picture for what I was talking about, that set point and normal range. Again, set point, this is just like the optimal, physiological value. Again, it's kind of like the thermostat. You set your thermostat at a specific temperature, right? The normal range is what's considered normal before you start having to worry about kicking things on. So normal range, again, just what's the high, what's the low, that's considered normal, and everything in between is normal. So if you go past, let's say in the picture, we go up, right, past this blue line up here, right, up in the white space here, then we're going to have to do something to bring us back down, right? Same thing if we were to enter into the white space down here, we'd have to do something to bring us back up, right? So as long as we're anywhere in here, everything's just fine, right? Everything's normal. and we don't notice anything. It's not until we start exceeding that, right, exiting out from this blue band to this higher point or lower point, that we start to notice something is wrong. And so really it comes down to two basic types of feedback loops. I've already briefly introduced these, but we're going to talk about them in depth. You need to know these feedback loops, by the way. Do not leave this class without understanding a feedback loop, because these feedback loops are massive. And we are going to see at least one of these over and over and over and over again. You will potentially be asked to describe these, to compare them against each other. So you need to know these two types of feedback loops, at least on a general level, pretty intimately. Definitely practice, study these. So we have two: the negative feedback loop and the positive feedback loop. Negative and positive here have nothing to do whether something is good or bad. Why am I saying that? Because I see that mistake made over and over and over again, where someone goes, negative feedback loop, that's got to be bad, right? No. Negative feedback loops just means that we are going to do something in opposite directions. Whereas positive feedback loops, some people go, oh, that's got to be good, positive, yeah. Not necessarily. All it means is we're going in the same direction. Think of it like if you were adding versus subtracting. Negative feedback loop is you're subtracting. You were going from a high number, now you're going back down to a low number. Positive feedback, we're adding. We have a high number, we add more to get an even higher number. That's the way I would think about it with negative and positive feedback loops. So again, what we're looking at with negative feedback loops, we are causing a change so that we can go in the opposite direction to the original change. With positive feedback loops, we have a change, and our body's going to cause a change that pushes us in the same direction. Right? So like if we were talking temperature, right? Like let's say we had a positive feedback loop for body temperature, and it started getting hotter and our body temperature increased. A positive feedback loop would cause us to get even hotter, right? And hotter and hotter and hotter, and keep going until we were really, really hot. So you can see with that example, right, because getting excessively hot is not good for you, right? You can't survive if your body temperature goes too high. So in this case, a positive feedback loop with body temperature is a bad thing, right? That's going to hurt you. So even though it's called positive, it doesn't mean it's always good. It just means it's a directional term, right? So we're going to look at the negative feedback loop in kind of up close. This is really the bread and butter of the feedback loops, because we're going to see the negative feedback loop a lot. Because a lot of things, you know, we want to stay within a normal range, and so you need something to, if you go too high, something that brings you down. If you go too low, you need something that brings you up. The negative feedback mechanism is perfect for that. So again, we're going opposite direction. If we go up, then the negative feedback mechanism brings us down. If it goes down, the negative feedback mechanism brings us up. And so again, this is really kind of what's doing the work in terms of keeping us around that set point. So we see negative feedback loops a lot. So again, I just reiterate right what I just said in the last one. Most of the things we're going to talk about are using negative feedback mechanisms. So what are some things that use negative feedback mechanisms to maintain homeostasis? Things like body temperature is maintained this way, blood pressure, your breathing rate, your heart rate, the glucose found in your blood, the salts we find in your blood, the carbon dioxide in the blood, the pH of the blood. This is just a short list of things that are regulated using negative feedback loops. There's a ton though, right? The calcium that we find in blood, right? Like all sorts of stuff. All right, but let's go ahead and talk through one of these so that we feel familiar with this. So in this case, we're looking at blood pressure. We're going to talk through the image here on the slide. So there's a stimulus, right? Something has changed right, in terms of the blood pressure, right? Blood pressure has gone too high, right, in this case. And so the baroreceptors, these are receptors that detect changes in pressure, they will detect that the blood pressure has gone up. And so we can send that information to the brain, right? The brain will make sense of that, going, oh, snap, blood pressure's up, right? Then we can send out a signal to some of these other blood vessels, like the arterioles, that will change what they're doing to help lower blood pressure. In this case, the dilation of the blood vessels, so widening them, right, opening them up a bit so that there's less pressure, there's more space for the blood to occupy, less pressure that the blood is under. All right, and so then we go, but blood pressure goes back to normal and everything's good. Now, if it was the opposite, right, blood pressure was too low, we would have a different set of actions that would happen. But the same basic setup would be there. That there would be a receptor that would detect blood pressure being low, the control center, in this case the brain, deciding what to do with that, and then effectors basically putting the brain's plan into effect, right, of how to bring blood pressure back up. Right, so you'll really want to get familiar with this, and you'll be asked to do things that, you'll be seeing these examples over and over again. So again, if you don't understand it perfectly now, that's okay, but you're not going to be able to ignore this, right? So don't think you'll never hear about this again and it's whatever. You will see this over and over again. It's going to be stamped into your brain forever. So we get positive feedback mechanisms. Again, this is where we're going. This is like what I call the runaway train, where we are pushing away from equilibrium. We are going in one direction until we get to a climatic event, right? Basically, we want to keep on going, get further and further and further away from normal until we reach this certain breaking point, the climatic event, and then we can go back to normal, right? Then we can come back down. And the best example of that is childbirth. There's some other things like lactation and blood clotting, but the one example that we always go over is childbirth and oxytocin. And so since that's the one we have the picture of, that's the one we're going to talk about. So you think about birth, that is a climatic event, right? That is very different from your normal day-to-day activities. It's very, very different from normal. And we want to, at some point, right, get that baby out of there. Right? You ask anyone who's ever been pregnant, they probably will have that same thing of, yeah, I was ready. I wanted that kid out of me, right? So, I mean, I don't know how frank they'll be about it, but it goes without saying. So, this person is pregnant. They're in labor. They're going to have a baby. What can we do to get the baby out? And that comes down to a positive feedback mechanism. So as this baby is pushing, and it's going to push on this cervix, right? It's going to push on that cervix, and there are little nerve cells there that are sensitive and can detect stretch. So that baby's head is pushing on it, which is stretching that tissue, and we have cells there receptors that can detect that stretching. We send that signal about stretching to the brain. The brain then is going to release oxytocin. Well, oxytocin is going to communicate with the effectors in the uterus, the muscles of the uterus, that will cause a contraction. Well, if the muscles of the uterus contract, squeezing around that baby, that's going to push the baby against the cervix even more. That's going to cause more stretching. More stretching. Stretch receptors tell the brain it's stretching even more. The brain then goes, oh snap, more oxytocin. More oxytocin makes its way to the uterus. Uterus gets that oxytocin and squeezes even more. Stronger contraction. More stretching as that baby's pushed against the cervix, and now we're probably even into the birth canal, right? That stretching, the receptors detect that, they tell the brain goes more oxytocin, the oxytocin causes uterine contractions, baby's pushed more stretching, more oxytocin, more contractions, more stretching, more oxytocin, more contractions. You can kind of see where we're going, right? We're going in the same direction, and we're going to keep doing this until we reach that climatic event, which is the baby's out, the baby's born, and all that stretching that was occurring because the baby was there has now stopped. And because the stretching of the cervix has stopped, the positive feedback cycle also stops, right? Because there's nothing to push against the cervix anymore to cause the stretching to keep the cycle going. So the positive feedback loop is something that happens in extreme cases like that, like childbirth. But for the most part, again, it's usually going to be a negative feedback mechanism. And that's to keep us within what we call normal ranges. Normal ranges are defined as basically 95% of the values from a normal population. So basically it's kind of like, you can think of it like an average in a way. Like people generally fall within these ranges, within these numbers. So we we look at 100 people, 95%, 95 of those 100 people are going to have numbers within that range. And just a few people will exceed that or be too low. And so we use this, what we call the normal range in a medical setting to basically say if this person's test results are normal or abnormal. Again, normal values, negative feedback loops are the ones that keep us within those normal values. So let's talk about some normal ranges, normal values of a few different things. So let's look at like body temperature. You've probably heard the 98.6. Yeah, okay. But does that mean if you're 98.9 that you have a fever and you must be sick? No, because there's fluctuations in that. Different people are maybe a little bit warmer, a little bit cooler. So the normal range is 97 to 99. We're not going to say that your body temperature is too low or too high until you are at like 96 or 100, right? As long as we are within 97 to 99, you're just normal. Same thing with blood glucose. Normal range is 80 to 110 milligrams per deciliter. You can fall anywhere within there. Some people may be closer to 80, others closer to 110. Within that range, though, it's all normal. And even within one person, you may fluctuate within this normal range based on maybe when you ate and what you ate. Blood pressure. We're typically looking at a systolic number of 90 to 120 over a diastolic number of 60 to 80. Right? So if someone has a blood pressure of 100 over 75, that's normal. If they have a blood pressure of 95 over 62, that's normal. 118 over 78, that's normal. It's all within normal ranges. 140 over 90, oh man, nope. We've left the normal range, right? 140 is over 120. 90 is over 80. This person would have high blood pressure. They'd be hypertensive. So now we get to signs and symptoms, right? So when we're looking at disease or disorders, we want to look at signs and symptoms. Signs are things that you as the healthcare worker observe or you measure. So you take someone's temperature, right? You can see a temperature, right? You can see a number on a thermometer. You see a rash, and you can describe the appearance of the rash. So a sign is very straightforward, right? It's objective in that you as a healthcare worker, a healthcare professional, you can say, this is what I observed. This is what I measured. A symptom is something the patient tells you about. I feel nauseous. I feel weak. I feel dizzy. I feel pain. Right? We can't measure those necessarily with a tool. We can't observe them with our own senses. We're relying on the patient to describe them to us. So look at our example here. We're looking at a concussion, right? So we have signs of a concussion on the left and symptoms of a concussion on the right. So signs of a concussion, the person's unconscious. Right? You can say, whoa, that person's they're knocked out. They're disoriented. They're not acting normal. Right? You can see like, oh, they're maybe not speaking correctly. They maybe don't remember where they are or who they are, right? They have a dazed or vacant stare. They can't remember things. You ask them what day it is and they can't tell you. Maybe they're calling you mom because they're confused, right? They're like, Mom, what are you doing? And you're like, I'm not your mama. Right? Those would be signs of a concussion because you would be able to objectively say, this person called me mom and I'm definitely not their mom, right? Or this person is speaking and it doesn't make sense. The person is unconscious. They cannot be easily roused, right? They're not waking up. Or it's Monday and this person cannot recall the fact that it is Monday. Symptoms would be what the patient tells you. My head hurts. I feel dizzy. I can't really concentrate. I hear ringing in my ears. I'm tired, right? The light is hurting my eyes, right? Those are all things that the patient would report to you and that they feel. So when we're trying to help someone, right, help a patient, we're going to be looking at these things together to determine the cause of why there's some sort of problem. Because some things cause them to have all these issues, right, to have these signs and symptoms. And the collective signs and symptoms can give us a picture, right, give us a window of why they're experiencing what they're experiencing. So another thing we want to talk about is illness, disorder versus disease. An illness is just when someone says, hey, this is how I feel. It doesn't feel good, right? So it's kind of a generic term. A disorder is a general term for any derangement of function, meaning like we can't do this thing or this doesn't function properly, but it's a general term versus disease is specific. Right? So diseases are this is a weird thing. Diseases are disorders, but not all disorders are diseases. Right? Because we don't always have the specific term to describe why someone like is experiencing what they're experiencing. Again, like the disorder is just like general versus disease, we're getting specific. There is a set of signs and symptoms that are very specific to that disease, to that illness, right? Versus disorder, it's very general.